happy to be here to share our recent research on millimeter wave radar sensing. So the title of our work is towards Spoofing-Resilient and the communication integrated millimeter wave radar sensing. And this is a joint work with Professor Parth from George Mason University. Okay, let me start with a brief introduction about radar sensing. So radar is a type of sensor that uses radio frequency signals to perceive environments. The data it generates, as shown in the right figure, is a spectrum which describes the distribution of reflection power from targets at different distances and velocities. Compared with other sensors, such as camera, radar sensing has many unique advantages, such as seeing through visual blockage, sensing around the blockage or non-offset sensing, sensing in the dark conditions, and the capability of coherent phase and velocity tracking. So given all these unique advantages, radar has been used in many applications, such as autonomous driving, robot navigation, smart home sensing, and even smart agricultural sensing. The most common radar we're using is FMCW radar. The signal it transmits is a chirp signal whose frequency increases linearly with time, as shown in the left figure. The FMCW radar measures the frequency shifts between the transmitted signal and the received signal due to the propagation delay. It then maps these frequency shifts to the distance and the velocity of the target. Specifically, as shown in the left figure, the frequency shift Fd represents frequency of distance. It is caused by the propagation delay tau. And the other frequency shift, Fv, represents frequency of velocity, is caused by the Doppler effect. So the principle of FMCW radar is pretty simple but effective in natural environments. However, there is still a problem. Say if we have an active radio device, which can apply a non-zero frequency shift to the incident radar signal and then reflect it back to the radar. Then the radar can also capture that frequency shift. Again, as shown in the left figure, now we have an additional frequency shift, FM, or frequency of modulation, caused by that active radio device. The problem is that standard radar signal processing cannot distinguish between the two types of frequency shifts. It means that the active radio device can carefully choose the frequency shift to create a peak in the radar spectrum that resembles the peak of a normal object. So the presence of these modulated frequency shifts causes two major concerns. The first concern is actually related to its application, which is known as radar backscatter communication. So these backscatter tags, including our previous design Uniscatter, can encode information in the radar signal and reflect them back to the radar so that they can communicate with surrounding radar sensors. This technology can be used in applications such as smart transportation. However, not all radars support backscatter communication by default. So the radar backscatter communication may cause interferences with most standard radars. And the second concern, which I think is more severe, is that the modulated frequency shifts can also be utilized by malicious attackers to conduct spoofing attacks against the standard radars. This figure is from a paper titled MmWave, and here the attacker's vehicle is conducting a spoofing attack by creating a ghost vehicle right in front of the victim's vehicle. So it may trigger the misbehavior of the victim vehicle's ADAS system and threat the victim driver's life. The state-of-the-art defense and detection of radar backscatters mainly rely on changing the chirp parameters of the radar. The most common practice is to alter the frequency slope of the chirp signals in a radar frame, as shown in this figure, so that the peaks generated by the backscatter are no longer consistent in the radar spectrum. However, this approach still has two limitations. First, it can only detect modulation in distance domain, but not in velocity domain. And second, these chirps with different frequencies cannot be coherently combined. So this scheme compromises the radar sensing capability in terms of sensing range or sensing resolution. Okay, so given this background, we ask a question in our paper. Can standard radar, without any hardware modification, detect modulated frequency shifts to avoid communication interference or spoofing attacks while preserving the radar sensing performance? And the answer is yes. In this paper, we propose SCR, spoofing-resilient and communication-integrated radar sensing for backscatter detection. SCR is based on our key observations that the delay-induced frequency shifts from natural objects and the modulation-induced frequency shifts from backscatters have tiny but critical differences. So we have two specific observations corresponding to the two domains of the radar spectrum, the velocity and the distance domain. Our first observation is related to the velocity domain, and we observe that the delay-induced shift from natural objects varies with the chirp frequency. In contrast, the modulation-induced shift from backscatter does not. It depends on the configuration of the backscatter and is usually constant. And we also know that the chirp frequency varies within a single chirp. So it means that the delay-induced shift also varies within a single chirp. So using this difference, we can distinguish between the two types of frequency shifts in the velocity domain. And to achieve that, we developed the chirp splitting scheme, where a chirp in the radar frame is split into two segments with different frequencies. As shown in this figure, we have the blue segment with the lower half of chirp frequency, and the orange segment with the upper half of chirp frequency. We then calculate the two spectra from the two chirp segments and measure the peak location shifts between the two spectra to detect modulation-induced frequency shifts. So here is an example. So here is a backscatter modulating the radar signal with a frequency shift of 1,500 Hertz. And it is held by a metal stand, so you can observe two peaks in this radar spectrum. To accurately measure the peak location shift, we further address two technical challenges. The first challenge is the low resolution of the velocity spectrum generated by standard Fourier transform. And the second challenge is the mixture of the modulation-induced and delay-induced frequency shifts in practice. So we developed algorithms to obtain this enhanced spectrum. So from this figure, you can observe that the peak from natural objects hardly experience the frequency shift. And in contrast, the peak shift of backscatter is more significant. So this way, we can distinguish between the two types of frequency shifts in the velocity domain. So that's our first observation. Our second observation is related to the distance domain. And we found that the modulation-induced shift in the distance domain causes Anderson effects in the velocity domain because they are essentially the same frequency shifts. In contrast, the delay-induced frequency shifts in the distance domain and the velocity domain are independent of each other because one is caused by propagation delay and the other is caused by Doppler effect. We further identify the necessary condition for the Anderson effect to happen, that is uniform chirp sampling. So by default, the radar transmits chirp signals uniformly with equal time intervals. So based on these observations, we developed the frame splitting scheme where we split a frame into two chirp groups with different sampling methods, the uniform sampling and the non-uniform sampling. We then calculate the two spectra using the two chirp groups. Because the modulated frequency shifts can only create a peak in the spectrum of uniformly sampled chirps, we can measure the peak magnitude differences between the two spectra to detect those frequency shifts. So here is an example. Here we have the surrounding natural objects and backscatter working. The first figure is the radar spectrum generated using uniformly sampled chirps. And you can observe the peaks from both objects and the backscatter. The second figure shows the radar spectrum from non-uniformly sampled chirps. So the peak for the backscatter disappears. If you further calculate the difference between the two spectrum, then the peaks for the objects are canceled out, and only the peak for the backscatter is left. So this way, we can reliably detect modulated frequency shifts in the distance domain. Okay, so that's a basic idea about SCR. And SCR also very easy to be integrated with standard radar signal processing. So this block shows the standard radar sensing process consisting of the spectrum calculation and the object detection, such as using CFAR algorithm. And we can simply expand it with two additional blocks, one for modulation detection in the distance domain and the other for the velocity domain. Okay. So we implement SCR using a TS radar at 77 gigahertz and a backscatter prototype, which consists of a Hall antenna and an RF switch. And we evaluate SCR in both indoor and outdoor scenarios and with different mobility conditions. Next, I would like to discuss several results reported in our paper. So the first result is about the performance of velocity modulation detection. So this figure shows the mirrored peak location shifts with different modulated shifts. And we found that the big shift is proportional to the modulated frequency shifts, and it achieves the maximum at the range of velocity frequency, which is 5,000 kilohertz in this radar setting. And the red figure shows the accuracy with different peak location shift threshold. And the threshold of 10 hertz can reliably detect frequency shifts over 1 kilohertz, which corresponds to a speed of 1.9 meters per second at 77 gigahertz. The second result is about the performance of distance modulation detection. Again, the left figure shows a mirrored peak magnitude difference with different modulated frequency shifts. And we found that peak magnitude difference increases with the modulated frequency shifts, which means that it's easier to be detected. And the red figure shows accuracy versus the threshold, and the threshold of 0.5 can reliably detect most frequency shifts in the distance domain. Then we further evaluate the impact of SCR on radar sensing performance. Because the only change made by SCR is the non-uniform sampling of the chirps, so all these chirps can still be coherently combined. It means that SCR does not degrade the sensing range or resolution of the radar. The two figures below shows the mirrored frequency, which is related to the frequency range, and the peak width, which is related to the sensing resolution, using different schemes. And the results of SCR aligns well with the results using a standard radar frame configuration. So this proves that the radar sensing performance is not degraded. Finally, we conducted two case studies, one outdoor and one indoor. In the outdoor cases, we consider the autonomous driving scenario, where we place a backscatter and an object near the stop sign, and then I drove a car equipped with a TS radar toward the stop sign. The two figures below show the mirrored peak location shifts and the magnitude difference as the vehicle approaches the stop sign, and the metrics for the backscatter and object can be clearly separated. This indicates that SCR can detect both velocity and distance modulation of and distinguish it from natural objects. In the second case, we consider a radar-based gesture recognition system. Here, a user is perform a gesture towards the radar, and meanwhile, attacker is injecting a frequency shift to the radar signal. The left figure shows the spectral graph with the user's gesture and the frequency shifts injected by the attacker. Because the attacker is usually far away from the radar, so they must conduct the distance modulation. The red figure shows the radar spectrum calculated using the uniformly and non-uniformly sample chirps, and the attacker signal clearly stands out. This indicates that SCR can detect attacking signal against the radar-based gesture recognition system. Okay, in conclusion, in this paper, we propose SCR, a spoofing-resilient and communication integrated FMCW radar sensing scheme. And first, we conduct a rigorous analysis of the radar sensing model to identify the differences between different types of frequency shifts. And then we design chirp signal processing and radar frame configurations for reliable detection of those frequency shifts. And finally, we prototype the scheme and validate its feasibility in various settings. Okay, that's all about our work. Thanks for listening, and I'd like any questions.
Okay, very interesting work, and this is Lemi from Hong Kong PolyU. I have two questions. First is about the attack model. So I'm curious that what is the attack accuracy of the existing attack model? Yeah.
So our motivation is actually based on previous research about backscatter-based attacking. So they can apply arbitrary frequency shifts to the radar signal to spoof like various distances and velocities. So I think that's pretty severe.
Okay, so this works, scan the frequency band and some other parameters to attack the radar.
Yes, for the attacking model, they usually have a eavesdropper to receive the radar signals and measure the parameters. And based on the radar signal parameters, they configure the frequency shifts and conduct attack.
Okay, I see. And another small question is, could you please elaborate more details on the aliasing effect? Yeah, I am a little bit confused. Oh. Yeah.
Okay, so it is mainly because that the frequency range for distance domain is much larger than the frequency range for velocity domain, as shown in this figure. And a frequency shift is in the distance domain is far beyond the frequency range of the velocity domain. And because so it means that if you treat each chirp signal as a sample, then it can be viewed as undersampling for the modulated frequency shifts. So that's why it causes the aliasing effect in the velocity domain.
Okay, I see. Thank you very much.
Thank you.
I have a clarification question. So in terms of the sensitivity of velocity domain detection, you mentioned 1.9 meter per second, is that?
Yes. That's the smallest, that's the lowest speed we can measure with a threshold of 10 hertz.
I see. This is the velocity shift from the actual object velocity?
Yes.
Okay.
Yes.
Okay, cool.
It's calculated based on Doppler effect.
Okay, cool. Thank you.
Thank you.
All right, let's thank the speaker again. Thank you, Qian.
Thank you.